Today we will discuss a high pass filter using IC741. If it comes to the introduction of a filter, we know that filter is a frequency selective circuit. Filters are of two types, passive filters and active filters. As we know, passive filters contains the components RC, RL and RLC. In active filters, we will have one more extra component where we are using an operational amplifier for the design of the filters. That is the main difference between the passive filters and the active filters. And if we see the advantages of active filters over passive filters, main advantage is the gain can be varied, and we don't find any loading problem because the input impedance of an operational amplifier ideally is said to be infinity, and practically it will be infinity, and output resistance of that one will be low is an advantage of an active filters. And active filters are also cost effective. Coming to the applications of the active filters, these active filters are mainly used in communication and signal processing circuits. They are also employed in wide range of applications such as entertainment, medical, electronics, etc. And we will go for different types of active filters. We know that basically they are classified into four, but here we have included one more, all pass filters. Basically we have four categories of active filters: low pass filters, high pass filters, band pass filters, band reject filters, and all pass filters. Each of these filters can be built by using an op amp as an active element, combining or the combination of RC, RL and RLC passive components. If we go for a high pass filter and response of a high pass filter, if you speak relating to a high pass filter will be a quite opposite arrangement of a low pass filter, okay, where it will attenuate lower frequencies and passes high frequencies, and band will be given by using cutoff frequency known as or represented by FC. The pass band of an high pass filter is above the critical frequency. If you see the actual and ideal response of a high pass filter, if you see this particular actual response, you can see with a gain roll off of minus 20 dB per decade response, here we will have the attenuation band. This band we call it as the attenuation band, or we can call it as a stop band. So in the ideal response we will find the stop band here, where the cutoff frequency here will be represented by using FL or FC you can represent, okay. After that we will have, basically we will have in practical characteristics the transition band. You won't find stop band and pass band, in between you will find a transition band. Here in the practical characteristics we will have this as the transition band, this as the pass band. Next, on the x-axis of this particular response we will have the range of frequencies what we apply for this particular circuit, and on the y-axis we will have the gain what we get from this particular filter. Basically by taking the passive components, the arrangement of an high pass filter will be of this type. We will find a capacitor followed by one resistor, where VSC is the input signal with a particular band of frequencies, and this particular band of frequencies we will be applying as per the design. This is the basics relating to an high pass filter response. Next, if you see the cutoff frequency in the sense, here we are designing a high pass filter, and we need to set up a cutoff frequency where we will find the cutoff frequency of that one and then go for design of R and C components. Basically, in the design of the low pass, high pass, band pass and band reject filters, basically C will be assumed as 0.01 microfarads and FC will be given in the question what we have, in the design what we have. For example, take if you want to design a filter with a cutoff frequency of 2000 hertz, FC will be taken as 2000, R will be taken as 0.01 microfarads and then we will be finding the value of R, and this value of R will be substituted in the equation, in the circuit diagram for obtaining the value of resistance. Same equation will be applicable for low pass and high pass filters. Next, if you go for the design of a active high pass filter, we can see here the value of R when it is equal to Xc, and we are representing Xc as the capacitive reactance. From that we will find the value of R, and from that we will be representing the critical frequency. Fc is equal to 1 by 2 pi Rc. This is the basic circuit by using a passive, only the passive components. And if you go for a filter which is an active filter, now you can see in this diagram we have included one operational amplifier. We know that it is having better characteristics, ideal characteristics such as high input resistance, low output resistance, high bandwidth, high common mode rejection ratio. All this makes that we can use an operational amplifier for design of some active filters. So this is the circuit arrangement basically for a high pass filter, and we know that the gain roll off rate will be of minus 20 dB per decade. One combination of R and C will provide you one particular pole. So if you use R and C components, these R and C components, we will have this particular pole here. So you can change the order of the filter and we can obtain the number of poles on that particular thing. Okay, so if you use an operational amplifier, you can vary the gain. The gain of that one can be given by gain A is equal to 1 plus, basically we will have a feedback resistor. Here feedback resistor is given by R1 and input resistance given by R1. Basically here they have represented R1 in the place of RF and R2 in the place of R1. Once we substitute the required values of resistances for the required gain in the circuit, gain can be varied for an high pass filter. Next, if you go for the design of that one, considering the bandwidth and all those things, we are going for the design of the high pass filter. So taking this formula, Fc is equal to 1 by 2 pi Rc, and following the design steps of a high pass filter, that is assuming the value of C, finding the value of R, and substituting the values of the gain resistors 1 plus Rf by R1 or 1 plus R1 by R2, we can obtain the gain of this one, where this variation of gain will provide or will make this particular circuit an active filter. And if you go for the summary for the design of a high pass filter, it is mentioned here that the low pass filter bandwidth, the band of a low pass filter is the same as the upper critical frequency. The band of a high pass filter extends from lower critical frequency up to the inherent limits of the circuit, maximum value you can have. So here they have represented the Butterworth filter response is very flat and roll off rate is of minus 20 dB. Next, a Chebyshev filter response has ripples and overshoot in the pass band, but can have roll off rates greater than minus 200 dB also. And when it comes to applications of the high pass filters, these are used in communications and these are also used in signal processing applications. Thank you.